Okay, any questions for the started? Okay. Okay, last time that if you have your favorite n by n matrix, call it A, what does it mean for lambda B? Lambda is a number and B is a vector. What does it mean for lambda B to be an eigenvalue eigenvector pair? This means that it means the linear transformation A, or the matrix A, however you want to think about it, works nicely on B. Essentially, at the end of the day, multiplying this vector by the matrix A is the same thing as multiplying it by a scalar. So eigenvectors are vectors on which the linear transformation is easy. So if I have an eigenvalue A, and I can find eigenvectors, right? And we went through this exercise quite extensively last time, because if you have AB is equal to lambda B, well, you can just manipulate this, massage it a little bit. That means that AB minus lambda B is equal to 0 vector. And I can massage it a little bit further. Here I'll put in, I can slip in the n by n identity, right? There's no harm in here because B is the same thing as I times B, but this allows me to kind of factor things out. So if I walk up to you on the street and I give you a matrix and I give you one of the eigenvalues, then what you do is take A minus lambda I B. So essentially you subtract lambda, whatever I gave you, off the diagonal elements. And to find the eigenvectors, you're looking at the null space of this big matrix here. Right? So if you look at A minus lambda I, then figure out that thing's null space, and that's going to give you the eigenvector, right? And that's kind of what we're doing. Now, in almost all my examples last time, I just walked up to you and said, hey, guess what? Here's a matrix and here's an eigenvalue. What I didn't tell you is where did I get the eigen? How do I figure out what that is first? Right? Well, here's the idea. How do you find these in the first place? Right, I just kind of handed them to you last time. Well, here's the deal. Let's look at that last equation here. We have suppose notice, as we pointed out last time, V makes this eigenvalue eigenvector equation. Well, if V is the zero vector, it always makes this work, no matter what rank, right? So it doesn't tell us much. So the interesting case is, if I have a non-zero eigenvector, then that means that the null space of this big matrix here is not trivial, right? Remember, the null space of this matrix right here always has the zero vector in it. But if it's got a non-zero vector, which that works, that means that there's something non-trivial, right? You got at least one free variable, right? What condition on this matrix? What condition on this matrix here guarantees that I will have a non-zero eigenvector? I'm sorry. When that is not. Okay, he's right. When this is not invertible, right, then this will guarantee that you've got a non-zero because you've got at least one free variable. But I'm a very simple-minded fellow. So can you give me a condition? There you go. If the determinant is zero, then you will get a non-zero eigenvector. And so this is kind of key here. This kind of answers your question. Eigenvalues are precisely solutions to determinant. So take this matrix here. You've got your original matrix A that you want to find the eigenvalues to. Take the determinant of A minus lambda I, and that will give you the eigenvalues. So actually, I gave you a bunch of eigenvalues last time. Let's go back and kind of recheck that. So, for example, let's check the get this. A minus lambda I. So this means A minus lambda times the identity matrix. So you're basically just subtracting lambda from the diagonal elements. All right, okay with me? And now let's hit this up. See what we get. We get minus 2 minus lambda, 5 minus lambda, minus 6 times minus 2. This should actually give me a polynomial on lambda, so I should be able to figure out what the eigenvalue is. Let's see what we get. This is going to be lambda squared. That's going to be plus 2 minus 5 minus 3 lambda. Then I'm going to have minus 10 plus 12. So that lambda squared minus 3 lambda plus 2. And this factors conveniently as lambda plus 1, or I'm sorry, lambda minus 1, lambda minus 2. So I get eigenvalues. 1. And I don't know if I used 2, but I certainly used 1 in the example last time. I said, oh, look, what an eigenvalue. That's where they come. Everybody okay? Let's look at that other example. Here. Let's extract the eigenvalue from this. Six. And minus 2. Okay, so suppose I just use this matrix and we want to extract eigenvalue. And so let's take the determinant of this and set it equal to 0. By the way, when you do these computations, be sure to be careful. I don't know about y'all, but I find it very easy to make a misstep. So be super careful. But again, when you get your answer, it's always check. Let's set this equal to 0. Let's see what happens. Well, I'm just going to plow this determinant. I'm just going to go right through it here. It's 4 minus lambda times the determinant of this little matrix here. Lower right box, 1 minus lambda minus 3 minus lambda minus 0. That was convenient. The next bit is going to be minus 0 times whatever that other one. You can follow it computing, right? Because gotta love 0 plus 6 times the determinant of this little box here, which is 0 minus minus 2 times 1 minus lambda. Now, let me clean this just a little bit. We stampede off into factor land. This is 4 minus lambda. 1 minus lambda. 3 minus lambda. Remember I said 0 minus, right, actually plus 6 times 12. Right, so plus 2 times 6. Where did I mess up? Yes, thank you. Thank you. I can get burned on that, so I appreciate that. Yes, got more than minus. Everybody okay with that? Now, who wants to multiply with that cubic? No volunteer for that, but there's a shorter way to do it. Anybody see something we can do? This is a common factor of 1 minus lambda. That'll make me feel easy. This leaves me with a more modest 4 minus lambda minus 3 minus lambda plus 12. So this is 1 minus lambda, and let's see, this is going to be minus 12 minus lambda plus lambda squared plus 12. So I got all kinds of up there. So the 12s cancel, and I get 1 minus lambda times minus lambda plus lambda squared is equal to 0. And I'm going to take one more little baby step. I'm going to pull a negative lambda out of this. And that makes it easy for me to pick my roots out. So actually I get 2 eigenvalues. I got lambda equals 0. I also got lambda equals 1 with multiplicity 2. All right. Okay, so I'm going to do a big one. But let me ask you this. Here's kind of a first observation. Can you give me an example? Is it true that I can always find the eigenvalues? The answer is yes and no, but it depends on what your restrictions are. Give me an example. Let me take this rubber sheet right here. It looks like somebody just accidentally kicked the identity matrix on the side and changed the sign. However, the subtle change makes things kind of interesting. So let's look at the determinant of minus lambda 1. Well, I subtract lambda from the diagonal there. And what do I get? Lambda squared plus 1 set it equal to 0. What are the eigenvalues? Yes. She is correct. Plus and minus I works. But there are no eigenvalues if I say you've got to restrict it to the real numbers, right? So I'll make a few about this. Because of course there is no real number as a solution to that equation. So this matrix right here has no eigenvalues, no real eigenvalues. Can somebody explain that? Geometry. So here I have an algebraic equation that just mindlessly tells me no eigen, no real eigen. Can somebody think of another way to tell this matrix has no real eigenvalues? What does this matrix actually do?
Swap x and y and make y negative.
All right, so let me see if I can get a picture of this. I'm going to see what the effect is on ordinary standard basis. This is 0, -1. That's 0. So remember, all you have to do to understand what a linear transformation does is see what it does to the basis. and everything from there follows. So what happens here? The basis element 1, 0, so this one actually ends up at 0 minus 1. There. And the basis element 0, 1 actually ends up at 1, 0. So what is this linear transformation doing? Uh, 90 degrees. Looks like what? Everybody agree with that? So there is no real vector that is just being scaled. They're all being rotated, right? So when I look at A times B, it just rotates B. It's never a multiple of B because it's just rotated at 90 degrees. Do I agree with that? By the way, in two-dimensional space, rotation of less than 180 degrees doesn't have an eigenvalue because there's no non-zero eigenvector. Everybody okay with that? Can you do something similar in three-dimensional space? Can you make a rotation such that there is no non-zero eigenvector in three-dimensional space? That's a little harder to picture, isn't it? But it turns out that if you do any linear transformation of three-dimensional space, you can't do a complete rotation. There's always some vector in there that is being scaled. That's not obvious, is it? You want to see why that's true? I'll show you why that's true. And I'll set up the computations like I'm actually going to do something, but I'm not really going to do anything except make an observation. If you have a linear transformation, but how about that's any linear transformation of three-dimensional space I can realize as a matrix. Does everybody agree with that? Now let's just suppose that I try to find out the eigenvalues. Everybody okay with that? So this is what I'll do to find them eigenvalues. I take the determinant of this and set it equal to 0. Right? Nobody wants to do this crap, right? But I can tell you what, without so much as batting an eye, I know that this will be I didn't compute it, but I know it will be a cubic polynomial. Everybody agree with that? And actually, because we've got minuses and it's an odd thing, it'll be minus lambda cubed, but that doesn't matter that much. And yes, there will be some lambda squareds in there. I don't know what they are. I'll call it A. And there'll be some lambdas in there, and there'll be some numbers in there, and I'll just call it that. Everybody okay with that? Now, this is a cubic polynomial. Does this thing have a real root? Every cubic, what happens when you take what happens to this as lambda goes to infinity? Lambda is very, very large. What happens to this? It goes to negative infinity. Everybody agree? Because lambda cubed becomes dominant. What happens if lambda goes to negative infinity? So let me draw a picture of this polynomial. It does a little dance in the middle, but for sure, it goes like this. And then you connect this, right? No matter what, you've got to cross the x-axis because it's a continuous function. Everybody okay with that? That means this thing always has at least one real eigenvalue, which means it has one non-zero eigenvector. So no matter how you try to twist three space, there's always going to, you can completely turn the plane. and have no non-zero eigenvectors. But in space, no matter how you try to move it around, there's always going to be some vector that's just being scaled or contracted. That's not obvious, right? But the algebra tells me everything. Can you generalize this? If I want to make a massive conjecture, yes. That is correct. If you have odd dimensional space, there will always be a non-zero eigenvector. If you have even dimensional space, maybe yes, maybe no. Four-dimensional space, you can do it without actually any eigenvectors as well. So that's kind of an interesting observation. Okay, any questions? This. So let me tie together some theorems kind of from. Let me point out something that I said last night. What if you have an upper triangular matrix or a lower triangular one? Well, if you look at the determinant, we'll call this A here. If you look at the determinant of A minus lambda n, this is the determinant of A11. And how do you take the determinant of triangular matrix, upper or lower? It's just a product of the diagonal. Y'all remember that? So this is A11 minus lambda, A22 minus lambda, and with ANN. Set it equal to 0. And so lambda, the eigenvalues are A11, A22. That is to say that the eigenvalues in an upper or lower triangular matrix are just you can just read them off the diagram. They're just the diagram. Okay. So here's a couple of theorems that I will record as your notes. We just stated this one. Theorem. Yeah. A triangle upper or lower. Then the eigenvalues of A are the diagonals. Here's another theorem. A is singular if and only if zero as eigenvalue. The reason for this is a matrix is singular again let me emphasize this. This is a square matrix again. A square matrix is singular if and only if its determinant is zero. And its determinant is zero if and only if determinant of A minus lambda I has a non-trivial null space, which means zero is an eigenvalue, and conversely. Here's another one. If A determinant of A is product of this eigenvalue. By the way, I should point out this works even if the eigenvalues aren't real. So here's a short example here. This matrix we found out had complex eigenvalues as I and minus I. And if you look at the product of the eigenvalues, and that's the determinant matrix. I'm not going to prove this one. You can just take this on faith for right now. Notice that this is clearly the case when A is triangle matrix, right? But might be a little bit more mysterious in general. So we'll worry about that later. Okay. Questions? Okay, so let me define something here. We're going to look next section at something called diagonalization. Let me define something. Definition. Suppose that I have two square matrices. I'll call them A and B. We say that A is similar to B. Yeah, there is an invertible. This matrix must be invertible, but this is nothing you have to memorize. I think once you see the definition, it's clear why that's invertible. Matrix P, also n by n, such that P inverse and P. So what it means for two matrices to be similar is if there's an invertible matrix P, since P inverse of A, P is equal to B. This is sometimes called a conjugate of A. Notice you could take P to be the identity matrix, and any matrix is similar to itself. If A and B are similar, if B and A are similar, this is actually a transit notion. That's just for those of you that are interested in mathematics of it. This is what's called equivalence relation. But when you have two similar matrices, say A and B, what that essentially means for square matrices is they're essentially, loosely speaking, the matrix is the same linear transformation with respect to different bases. We're going to go over that. We're going to go over that a little more carefully later. But here is something I want to emphasize. Here, if A and B are similar, then A and B have same characteristic polynomial. Let me make this precise. Yes,
Whenever you do P inverse AP, isn't that just A?
No.
So
Because
P inverse times P.
if A and B commute, you're assuming that you can turn A and P around. You can't necessarily. Right? So I'll give you an example. What is the characteristic polynomial? This is the characteristic polynomial. When you work out that determinant, then it's polynomial you get, and to have the same characteristic polynomial, then you get the same thing with both A and B. And A and B have same eigenvalues. Because you get the same characteristic polynomial. Let me quickly outline why this is true. A similar B. Then B is equal to P inverse A. So let's do the characteristic polynomial thing. B minus lambda I is P inverse AP minus lambda I. Okay, I need to massage this. This is P inverse AP minus lambda I P inverse B. Right, the only thing I did in that last step was I just put an extra P inverse P, which is sort of nothing. Right? And this is P inverse AP minus P inverse lambda I. Because you can put the identity in constants wherever you want, you can move them around. And this is P inverse AP minus lambda IP. Pulling P inverse out of this side, and I'm going to pull P out of the other side. I get that. So at the end of all this computation here, I got, well, is that. Now take the determinant of both sides. Now, what can I do with the determinant? I've got a product of three things. Larry, Curly, and Mo here. What can I do with the determinant of these three things? Say which one before. I can split them up, right? And notice, these are no longer matrices. These are numbers. And so this and this cancel out because this is determinant of A minus lambda I times determinant of P inverse. So I can put this back together. P inverse P And this is the determinant of the identity matrix. Right? The reason I can turn these around here is because the determinant, that's just a number. So here, determinant of B minus lambda is the same thing as determinant of A minus lambda. That means these two things have the same characteristic polynomial, and hence, right, and so they have the same eigenvalues. Multiplicity. Okay, any questions? Yes.
So on the middle blackboard, when you wrote P inverse AP, the second line on the bottom line, right there. You separated P inverse from P on the second term.
Right. Like that?
How were you able?
Because the identity commutes with everything, and so does any number. Right? So if you have two matrices A and B, it's not necessarily true that A times B and B times A are the same thing. Different order gives you different answers. But with the identity, you can do that. Doesn't matter what order you put. So right here, what I did was I took this guy and put it out in front. The reason I can do that is because that's the identity matrix, and that's just a number. Right? But you're right to question that. Because in general, you can't do that. That was Matt, your question earlier about aren't they the same when you look at P inverse AP? That's not true because I don't know that I can turn A and P inverse on. I do know I can turn P inverse in the identity. So actually, let me give you an example. And this is kind of an example, so one hazard. So here's an example. Let's call this A. Now let me think of an invertible matrix here. Let's draw something. 1, 2, 1, 1. That's an invertible matrix. This determines 1, right? Anybody know what P inverse is? Yeah. That smells right. Yeah, that looks right. Good. Thank you. Right. So she used that formula. That. So if you look at these two matrices, they're similar. That is, if you look at P inverse, two minus 1, P equals that. Right. So let's just troll this out. I'm gonna play the first two first, and I get that's going to be 2. That's going to be 1. It's going to be -1, 0. Now multiply this. This is going to be 2 and 1 is 3. This is going to be 2 and 4. This is going to be -1, and this is going to be maybe I missed it. That's going to be -1. 3, 4. This matrix and the original matrix are similar. They have the same eigenvalues. By the way, what are the eigenvalues? Can you just look at this one and tell me? 1 and 1, right? It's got 1 with multiplicity 2 because it's going to be 1 minus lambda times 1 minus lambda, right? This one will have the same eigenvalues as well. Notice this matrix looks different than this. Right? Now here's my caution. So the same character as a polynomial. And eigenvalues. Because think about what is the character of a polynomial? Notice this one gives 1 minus lambda squared, and this one also gives 1 minus lambda squared. Everybody agree with that? Because of the 0 right here, this one doesn't really make a difference. You see, you get the same character, right? Everybody okay? So both of these matrices, both A and C, have only the eigenvalue 1, multiplicity 2. Everybody okay with that? But they're not similar. Can somebody explain why they're not similar? Yes. And compose the matrix such that the inverse times A, P, C. No, there's not. How do you know? It's the old classroom question psychology, right? It's got to be no, right? And actually, it is no, because what's another name for the matrix A? The original A? It is the identity. So this is the 2 by 2 identity. So if you look at P inverse I2P, this is P inverse P, which is I2. And this is not equal to C, because C is not the identity because it's got that extra 1. So the moral of the story is to say 2 matrices are similar is a stronger statement to make. If you have 2 similar matrices, it is true that they have the same characteristic polynomial and the same eigenvalues. But you can have matrices like these 2 that have the same characteristic polynomial and the same eigenvalue, but they're not similar. I will leave you with an exercise, probably, and actually, maybe I'll be nice and start you off on this. Cause A, 1, 6, minus 19, 1. Oh, I'm sorry. 1 to 11. 1, 0, minus 4, 3, 1, negative 2, 2, minus 1, and 1 minus 4, 6 minus. Fine. Yeah, you guys do this. Some of you might practice this by throwing it into MATLAB or something like that. But how would you do this? Okay, somebody very concisely explain to me why this is going to suck. What's going to be awful about this? Yeah.
Have a lot of skills.
Yeah, look at this, right? Now I've got to do this determinant, right? Which is just awful. If I agree with that, it's awful. Anybody recommend something like these? Yeah.
Elegant decomposition.
Oh, then I got to look that up, right? Yeah, I mean, maybe. But how about another way to work this out? I would actually, so here's kind of my hint. I would take this row, basically focus on the fact that minus lambda is the easiest. And I would use this 1 to move all of this right? Times minus 1 1/2, times minus 1 1/2, and then times lambda minus 1 1/2. You'll have to multiply through by lambda minus 1. And what you'll have now is a 1 here and all zeros here, and expand about this column. And then that'll reduce it to a 3/3, which is easy. I got the following eigenvalues. I got plus or minus 2i and plus or minus I. See if you can come to that conclusion. So in a certain sense, this is a 4-dimensional matrix that only does rotations. There are no real eigenvalues. Okay, any questions on that? All right, I'll set you next week for Friday. It'll be out sometime later this week. And I'll be in my office. Got any questions?